Hello everyone, I'm Oscar Ibáñez from the University of Coruña in Spain. However, today I'm presenting the work mainly developed by a group of researchers from different departments of the University of Granada, and it's a spin-off the company Panacea Cooperative Research. Within the next minutes, I will try to summarize our outcomes in the automation of craniofacial superimposition with the goal of developing a set of methods that fully automate it. Craniofacial superimposition is an identification technique involving the comparison of antemortem facial photographs with 2D or 3D images of one or more unknown skulls. It is based on the hypothesis that the skull is unique, and the comparison is usually guided by corresponding anatomical landmarks, similar to the way fingerprints are used in dactyloscopy. The high availability of the materials required means that it has the potential to be used in a higher number of scenarios than other identification methods requiring expensive analysis and more complicated acquisition of materials, as the case of the DNA. However, its prevalence as commonly employed identification technique has been hindered by the lack of objective, reproducible, accurate, and automatic approaches. This has also prevented researchers from conducting robust reliability studies, limiting them to small samples and impeding their replication. So, what we have been doing during the last 15 years is to try to automate the technique to gain objectivity, accuracy, and the possibility to perform large reliability studies. In this slide, you can see our approach to craniofacial superimposition composed of the following stages. First, the selection of facial photographs and the automatic location of cephalometric landmarks in all of them. At the same time, we automatically perform subject to camera distance and facial pose estimation. Second, we scan the skulls and the mandibles separately and locate craniometric landmarks in all of them. After this, we also automatically estimate soft tissue depths. The third stage implies the automatic superimposition of the 3D skull over each facial photograph, following a camera calibration approach guided by the previously located landmarks. Finally, for each craniofacial superimposition case, that is to say one skull and one antemortem case with one or more photographs, the algorithm provides a score that can be employed for ranking candidates. Additionally, this fully automatic framework can be employed to calculate a likelihood ratio for each candidate, as we can automatically calculate the same score of a given antemortem case with a set of skulls with similar morphometry to the skull under study. This is really useful to provide statistical support for decision-making as commonly employed in other forensic fields such as genetics, voice, or facial recognition. In the following slides, I will introduce the main features of each particular automatic method I have just summarized. The first one is the cephalometric landmark location algorithm, able to locate 30 landmarks automatically. In this case, we have developed a deep learning-based approach which has been tested on more than 200 photographs with large variability in resolution, quality, pose, and camera employed. The accuracy of the algorithm, measured as the average Euclidean distance once all picture has been scaled to the same resolution, is below 4 pixels. This error is competitive to inter-expert dispersion error, as the box plot in the slide shows. Next automatic algorithm is the subject to camera distance estimation. This is again a deep learning algorithm, so again, as in the previous case, the only input data is a photograph, and the output in this case is the estimated subject to camera distance in centimeters. We have trained these machine learning methods with two different sets of data. On one hand, 150,000 synthetic images obtained from different 2D projections of more than 300 3D facial models, and on the other hand, 20,000 photographs from 28 different individuals. In all cases, we have used 4 different focal lengths, and pictures have been acquired at 12 different distances, from 50 centimeters to 6 meters, as depicted in the image. Additionally, the pose of the subject varied 180 degrees with neutral and smiling facial expressions. We plan to publish this data and the algorithm once the publication is accepted on a journal paper and is under revision for some months already, so I hope we can publish it soon. The accuracy of the algorithm is quite impressive, with an average error lower than 6 centimeters, and more important, a facial distortion error estimation lower than 0.2%. That is to say, bigger errors occur at bigger distances where perspective distortion effect is smaller. This behavior is observed in the graph at the right bottom of the slide. In comparison with Carl-Stefan methods, which is one of the state-of-the-art methods, it is more accurate and do not require any landmark location. This method could be really useful in craniofacial superimposition, but also in facial superimposition, or to develop photogrammetry methods able to estimate 3D facial distances and indices from images. The problem of estimating facial pose in photographs has been tackled by many different researchers, with means estimating errors ranging from 3.6 millimeters to 6. All these approaches are again based on convolutional neural network, the most common deep learning approach employed for regression methods in images. As in the previous case, this allows us to improve the accuracy, reliability, and explainability of craniofacial superimposition methods, and can be employed to improve again facial comparison and photogrammetry approaches. The next automatic method is able to accurately locate 58 craniometric landmarks in 3D scale models. It combines an initial stage using the open source library called MeshMonk and 5 geometric heuristics we have defined to refine the position of different groups of landmarks. Again, the accuracy is competitive with forensic experts, around 2 millimeters of average error. Unfortunately, as in the case of the location of the cephalometric landmark, there is not possible ground truth data, so the method accuracy is compared with the mean location provided by 3 practitioners. However, subjective visual analysis of the automatic results indicated even algorithm superiority to human operators. If you are interested in knowing more about this method, a journal paper has been already published explaining all details, and you can see the reference on the right bottom corner of this slide. Okay, once a set of craniometric landmarks are located in the 3D scale model, we can apply a facial soft tissue thickness estimation method instead of using the average distance of a given sample. In our opinion, it makes sense to estimate soft tissues for each particular scale instead of using average distances in the field of craniofacial superimposition, as we are trying to identify, that is to say, to establish uniqueness. We have initially performed one study using a reduced set of 30 input landmarks over a set of 500 subjects. These cases were provided by Pierre Guillemarc, and the data consist only of cranial and facial 3D coordinates of the landmarks. We tried different classical machine learning approaches, significantly improving the average estimators as depicted in the table on the 10 landmarks estimated. We are now developing a new, more challenging study over hundreds of CT and CBT scans, trying to estimate not only the depth but also the soft tissue direction, assuming that it's not completely perpendicular and can vary between craniometric and cephalometric corresponding landmarks. This data would be really useful to improve the performance of automatic scale face overlay method in the near future. And here we arrive at the last step, the automatic superimposition of the 3D scale model over the photograph. Our approach is to consider the problem as a camera calibration problem where the parameters of the camera used to take the photograph must be estimated. We have already published several papers on this regard, and you can visit, for example, a Skeleton AD webpage for a visual explanation of the camera calibration problem. Our new proposal improves our previous ones thanks to the integration of a priori information. That is to say, the focal length employed once we can extract it from the metadata in the case of digital photograph, the subject to camera distance estimated using the deep learning approach mentioned in some slides before, and the soft tissue estimation. In these two cases, we feed the algorithm with a range of possible subject to camera distances and soft tissue thickness, using the estimated measures and the percentile 95 error. We have also included a simple modeling of the cephalometric landmark location error. As explained at the beginning, an automatic method allows the application of craniofacial superimposition as a shortlisting tool, and we can provide a ranking of all the possible candidates automatically. In addition, we are exploring the application of likelihood ratio for the first time in the field. Using craniometric indices, we select a corpus of similar skulls from our database and compute likelihood ratio performing craniofacial superimposition over all those skulls. This way, we can give a statistical parameter concerning the possible match of a given skull with a facial set of photographs of the same subject. In this slide, we can see preliminary results of the new skull face overlay algorithm using a priori information to reduce the camera parameter search space. Using a subset of 78 cases out of the 500 from Guillaumard data and 17 pairs of corresponding llamas, we have simulated 20 photographs from each facial CT scan with different camera parameters and superimposed all the simulated antemortem cases with the 78 skull CT, making a total of more than 120,000 cross comparisons. We have performed different experiments using the real soft tissue direction and introducing 15 degrees of errors, and always assuming 25 pixels area of error for the cephalometric llamas. We have calculated the average ranking using one single photograph, resulting in ranking 2 and 5 for the cases of soft tissue direction being real and assuming an error in that direction, respectively. And we have also calculated the ranking using two photographs of the same person, which improved the ranking to 1.33 and 2.31, respectively. The graph in the right side of the slide shows the shortlisting capability of the skull face overlay approach. For example, if we only consider the top first of the ranking, in this case, that means the first individual, there are only 78, in 40% of the cases, so in almost 50,000 cases, the first ranked individual is the positive identification. Well, I forgot to mention that these preliminary results did not employ the soft tissue thickness estimation algorithm, so it employs the mean magnitude instead. So this is one of the potential improvements together with the new soft tissue depth studies we are developing, which are dealing also not only with the depth but also with the spatial relationship between craniometric and cephalometric llamas. So finally, all these developments are being integrated in the commercial software SkeletonID. In this animation, you can see a simulation of what the craniofacial superimposition algorithm is doing for each pair of 3D skull model and facial photograph. Thanks so much for your attention. I hope you enjoyed the presentation. You can write me whenever you want to ask questions, curiosities, or just get more information about our work. We have published different papers along these 15 years, and we are developing much more. So I will be really glad to provide any kind of information so you can make use of this research. Bye-bye.